Okay, the next transformation is transforming graphs when you have a number multiplying the front of the function. So, for example, if we have f of x, we want to know what the graph of k f of x looks like. So remember the explanation to this, since I made a little bit of a mess of this, the explanation you'll find at the bottom of example 3. It says that if we have the graph of y is equal to kf of x, this graph gets stretched if we multiply the function by a number bigger than 1. So it gets stretched for us, it gets stretched vertically. It gets compressed vertically if we have a number in between 0 and 1. So the two examples that I've got here is I want to sketch the graph of 2 times f of x. I'm going to do that in red, and I'm also going to sketch the graph of y is equal to a half f of x. I'm going to do that one in blue. So remember the principle of what I've been saying through all of this. If the number is on the outside, it affects the y, and the x stays the same. If the number is inside the bracket, it affects the x. The y stays the same, but you do the opposite to the x. Now nothing is happening here inside the bracket, so we don't need to worry about that. We only have one transformation happening each. It's on the outside. So what's going to happen here for the red graph is all we're going to do is just multiply all of our y values here by 2. Meanwhile, we will keep the x values the same. So, as usual, the best thing to do is to write down the coordinates and then transform them. So, for this, we're multiplying all of the y values by 2. So, minus 6, 0. Remember, we keep the x the same. So, minus 6, 0 is really just going to stay as minus 6, 0. Because 0 times 2 is just 0. Minus 2, 4. It's going to be minus 2, 8. 0, 0 stays as 0, 0. 2 minus 2 goes to 2 minus 4. And 4, 0 stays as 4, 0. So let's plot those points then. So minus 6, 0 stays the same. Minus 2, 4 goes to minus 2, 8. I'll put it approximately here. I've got a maximum turning point on it. 0, 0 stays the same as 0, 0. 2 minus 2 goes to 2 minus 4. And 4, 0 stays the same as 4, 0. So now we just go ahead and sketch that. So the more you stretch a graph, the sharper the gradients become. So this is going to come down here like so. It's going to turn and go up. It's then going to come down back through 0, 0, turn sharply here, and then go back up. So that there is a graph of y is equal to 2 times f of x. The next one that we're going to sketch is the graph of a half f of x. So again, we have the half on the outside, so it's going to affect the y's, but the x's stay the same. So let's have a wee look at that. So again, minus 6, 0, when we halve 0, it stays 0. So minus 6, 0 stays as minus 6, 0. Minus 2, 4 becomes minus 2, 2. 0, 0 stays as 0, 0. 2 minus 2 goes to 2 minus 1. And 4, 0 stays as 4, 0. So let's plot those points then. So we have minus 6, 0 staying here. Minus 2, 4 goes to minus 2, 2. Zero, 0 stays as is. 2 minus 2 goes to 2 minus 1. And 4, 0 stays as 4, 0. So when we have this idea of compressing the graph, because we're multiplying by a number between 0 and 1, and not including 0 and 1, when we compress the graph, that tends to flatten it out a little bit. So that means that we have a graph that looks something like this. And that there is a graph of y is equal to a half f of x. So note for this, if we have the graph of f of x, multiply it by 2, it stretches the graph horizontally, it gets to higher peaks and lower troughs. If we multiply by a number between 0 and 1, not including 0 and 1, then it starts to flatten the graph out a bit, and the peaks and troughs get a lot more closer together.